Bolt failure and joint failure safety factors require that we calculate the bolt and the joint stiffness. So how do we get those stiffnesses? Well, here's a figure 8-7 from Shigley, and it's definitely worth pausing at some point and trying to absorb what's in this table in some detail. I'm going to blow this up a little bit. Here we have the bolt inside, or clamping two plates together, and there's a washer that's used underneath the nut head. So a number of definitions here. Well, D is going to be the nominal fastener diameter, and there's a certain amount of the bolt that is within the joint between the nut head and the bolt head. So that total distance, lowercase l, let's call the grip. All right, so lowercase l called the grip, the joint length essentially, which includes any washers that you put in there. So here T is the thickness of the washer. There is, chances are, there's going to be a portion of the bolt within the grip that's unthreaded, and that's going to have a certain shank length LD. So the shank is the unthreaded portion. And then there's going to be a certain threaded length, L sub T, inside the joint. Now capital LT, that's the total threaded length of the bolt. And that's given in this Shigley table. So for inch and metric series bolts, we have the total threaded length, which is from the end of the bolt, which may or may not be inside the bolt. The end of the bolt should not be inside the joint. Best practice is to pick your bolt so that there's only one or two threads protruding beyond the nut. Anyway, we can get the total threaded length 2D plus 1/4 inch for bolts less than 6 inches, and 2D plus 1/2 for length greater than 6, etc., where capital L is the total bolt length, measured not from the top of the bolt head, but from the underside of that little washer that's built into the head of the bolt. And H is the thickness of the nut, and those are tabulated. If we have a bolt going into an internally tapped hole, we see the bolt actually ends right here. So we have L, capital LT, once again, is the total threaded length of the bolt, nominal fastener diameter D. The two plate thicknesses are given as T1 and T2. Nut thicknesses again, washer thickness is again given as T, and H is the dimension from the underside of the bolt head, top of the washer, to where the plates join together. And let's see, we have, now the question is, exactly how far do you go with the grip? The grip is not generally taken to be the entire length of the bolt inside the second plate, because we know that the bolts don't share the threads don't share the load equally. So there's an effective grip length L which goes a certain ways into the second plate, but not all the way. And it's given here in the table. So for figure A, which is the bolt going through, L is the thickness of all the material squeezed between the face of the bolt and the face of the nut. However, for figure B over here, L is H, which is the distance to the plate interface, plus thickness of the second plate divided by 2, or D over 2, depending on whether or not the thickness of the plate is greater than or equal to the nominal diameter. So these are things which, this doesn't sound like exact science, and it's not. It's engineering that works. Now, as we're going to see shortly, sometimes people want to get a bit more sciencey about these things for applications where getting a really fine point on these issues is extremely critical. Anyway, fastener length. Fastener length, total length, is going to be equal to the grip L plus H. That's the minimum fastener length that you need. And you typically have to round up using something like Shigley table A17. So L plus H takes you from here to here. That's the ideal bolt length. Round it up to the nearest one. That's just big enough. You want a couple of threads protruding. You don't want the threads not reaching the end of the nut. Fastener stiffness. Well, the bolt, we can view that as two springs. We can view it as a spring with a stiffness Ks, which is stiffness of the shank. Okay, and that Ks is going to be, well, always remember, if you have an axially loaded rod subject to a force P, it's got an area A, and it's got a length L. And if you apply that force, it's going to deflect. So there's the deflection. Deflection equals PL over AE. That means that the stiffness is force over deflection. I shouldn't call that P because we want to call the external separating force P. Call it F. Stiffness is F over deflection, which is going to be AE over L in general. So for the shank specifically, AE over L is going to be the A corresponding to the major diameter. Okay, so there's major diameter area AD, which is pi d squared over 4. E is the Young's modulus, and L is going to be the L sub d. That's the length of the shank. They use L sub d because the sub d means it's the length where the diameter is actually the diameter d. Now we've got another spring in series here, which goes to approximately there. It's got a stiffness KT, K corresponding to the threads. And that's going to be a tensile times E over L sub T. If the two springs are in series, KB is going to be 1 over the shank stiffness plus 1 over the thread stiffness. And when you combine these things together, you get the expression that's down here. KB is major diameter area times tensile area times Young's modulus over ADLT, which is the threaded length within the grip, not capital LT, plus tensile area times the shank length. So you should be able to confirm that by substituting the expressions for Ks and KT into that series spring stiffness formula for KB. Now the bolt itself, or the bolt head itself, the assumption is typically that the bolt head is rigid. Now the bolt head can also deflect a little bit. And I'm going to try to show that. I've got a bolt where I've sort of made the head kind of artificially deformable. Alright, so let's assume that the pink foam here is the bolt head, and here I have little shank length, threaded length. I'm going to put this bolt in a hole, and when I pull down, you're going to see that the bolt head is going to have some deflection. Okay, this bolt head thickness is going to contribute a little bit to the overall length of the bolt, and the longer the bolt, the lower the stiffness. Let's get back to my notes here. Okay, so Shigley doesn't mention this, but experiments by a guy named Cornwell from the Norton text, they say to make the bolt stiffness equal to 1 over 1 plus bolt diameter divided by length. So this is based on experiments to try and figure out how much the bolt head thickness contributes to the overall bolt length. There's a book by Hamrock where they simply put a little bit of a correction factor on the shank length. They use something like the L sub D. They add like 0.4 or 0.5 times the bolt head thickness, and that brings the stiffness down a little bit to account for that head deformation. On the website, I've posted a paper where some researchers from General Electric Healthcare got really concerned about this because they were using various kinds of bolts in the medical equipment. They talk about the N factor, which is that fraction of the bolt head thickness that you apply to lower the stiffness. They did a lot of experiments and some analysis And their finite element analysis was done for not just hex head bolts, but also for some specialized bolt heads, such as countersunk. And when you get really right down into the nitty-gritty of this, imagine that you've got a nice countersunk bolt on a piece of expensive medical equipment, and you don't want it to flex because you've got a manipulator that has to position something like a scanner or a surgical tool extremely precisely. There's going to be variations in the shape of the hole and the nut head, or sorry, the bolt head. Here we have contact here and here, which is going to give us a different stiffness than if we have contact here and here. So not only do some researchers do a lot of finite element analysis to get at the actual stiffness of a bolt with a particularly shaped head, but they do a lot of statistical modeling and come up with mean and standard deviations for those stiffnesses. So here we see some of the histograms for stochastic hex bolt and flange bolt end factors. So they're trying to come up with a confidence interval on what that real stiffness is going to be. I've posted another paper where the same authors look at bolted joints in general using FEA and stochastic random statistical methods. And this will make sense to you now, and now that we've learned a little bit about bolted joints. They do some FEA analysis where they look at the distribution of the von Mises stress at the bolt head fillet, and that's a critical failure zone often for fatigue, which will be a later topic. Here's a bearing stress profile, and they even talk about the threads taking the load in an uneven way. So those papers are posted for your interest. Excuse me. Turns out the joint stiffness, that's a bit more complicated. Here are some figures from the Norton text, FEA analysis of plates clamped by a bolt. What we see is, well, the bolt would be over here, and this would be the bolt. So we're seeing, I guess, the clamp material on one side of the bolt if we cut a section through the whole assembly. What people have noticed is that there's a tendency for deformation to occur along what looks like a conical pressure region. Something that we're not going to talk about in detail, but which is an issue, is if you have bolts that are a long distance apart and you've got a long span of compressed material in between the bolts, then this deflection of the material can actually open up gaps in between the bolts. So we're predicting what the safety factor is for joint separation around the bolt, but you've got to use enough bolts so that you don't lose your safety factor due to this kind of deformation away from the bolts. So make sure your bolts are not too far apart, but don't put them too close together or you're not going to be able to get a wrench in between them. So joint stiffness is done by estimating the deflection due to compression forces radiating outward from the edges of the bolt head or the washer. And it occurs typically along a 30-degree line approximately. Different researchers have found different angle values. So let's look at what's called a frustrum. Okay, so frustrum, plural is frustra, that's one of these little truncated cone areas. So we have the nominal diameter D of the fastener. The underside of the bolt head is going to have a little built-in washer which is going to have a diameter D sub W, which is typically 1.5 times D. So for our generic frustrum here, we're going to use big D as the diameter, the smaller of the two diameters, the diameter from which those compression forces radiate outwards. So big D here is bigger than little d, and big D is equal to D sub W. We have this radiating outward along a 30-degree line, and then at some differential slice of the frustrum, at some distance x down from underneath the bolt head, we have this little dx slice. Now this little slice, it's a trapezoid, but if it's close enough to approximate it as a little cylinder, and the deflection is going to be P times the length of that little differential element over AE, similar to what we described for the bolt stiffness. Now the element area, it's going to be a ring. So, that's actually got a shape something like this, with whatever the diameter is. Let me draw that a little better. So it's going to be a ring with whatever the diameter is at the differential element, and an internal diameter d. So the area is pi times r outer squared minus r inner squared. And r inner squared is going to be simply little d over 2. How do we find the big diameter? Well, we have an angle alpha, and we're looking for this little dimension. That little dimension is going to be x tan alpha. So that's going to make this big diameter d plus 2 of those x tan alphas. Alrighty. So the area is going to be pi times outer radius squared minus inner radius squared. And we can rewrite that as RO minus RI, RO plus RI. For some reason, I'll never forget from grade 9 algebra, x minus y times x plus y equals x squared minus y squared. So, same thing here. So we have RO minus RI, d plus 2x tan alpha over 2 minus the inner diameter, which is d over 2. So we divide through by the 2's. We can see we have d, big D minus little d over 2 plus 2x tan alpha over 2. So that gives us that term. And then the RO plus RI will give us the other term. So there's the area. We're going to substitute the area equation into the differential deflection equation. We're going to solve for K of the frustum, which is P over d delta. And we're going to integrate. And without going through the integration details, the stiffness ends up being, for a generic single frustum, pi, Young's modulus, bolt diameter, tan alpha, over the natural log of 2 times t. T is the thickness of the frustum. We have big D, and big D is the, again, it's the smaller of the 2 frustum diameters, typically equal to the washer or the bolt head width. And all those things go into the bottom here, and we get equation 819 from Shigley. If we substitute in the typical 30-degree pressure angle, then tan alpha gets subbed in there. We got 0.5774 on the top, and the 2t tan alpha becomes some number times t. If you have 2 clamped members that are the same material, let's see here. So I'm going to have 2 plates with the same material. They don't have to be the same thickness. Let's say the grip is equal to lowercase l, and we have dW equal to the washer diameter, which is really the underside of the bolt head. Okay, so that's D, which equals dW, which is typically 1.5 D. All right. The frustra come out like this. They go through the place where the plates join, and then we've got a nut head on the other side, and we're going to have this symmetric pair of frustra. So here's frustrum 1, frustrum 2. This is going to be, a K frustrum 1, and that's going to be a K frustrum 2, and they're going to be equal because they have the same Young's modulus, the same thickness. Again, we're ignoring where the plates actually join together. The thickness of the frustra is the distance from the bolt head to this dashed line going across there. Okay, so we're looking at 2 frustra with the same thickness, the same Young's modulus, the same stiffness. It's easy to combine 2 identical stiffnesses in series. And if you do that, you get the overall total joint stiffness. Okay, the K up above for the single frustrum, that's for one of these 2 trapezoidal frustra. All right, one of the two. This Km is for both. And that only applies if you've got two clamp members of the same material. Now if you make the substitution where dW equals 1.5d, I won't put that down here because it doesn't always apply, but if you make that substitution, and if you substitute alpha as 30 degrees, then you get a very simple expression for your Km for two plates of whatever E they have, same material, joined together. The safest approach is to use 820 and do it for individual frustra. So down here we have the worst case scenario. We have a nut and a bolt. We have a washer which increases the grip length. Okay, so the total grip length is going to be, don't forget to put the washer in. Now, example 8.2 in the textbook does a very good thorough treatment of the calculation of the joint stiffness for this particular example. But I just want to show a few things here. This 0.75, okay, that is this dimension here. That's the 0.75. So it turns out that even if you put a washer underneath the bolt head, you don't have the frustra radiating out from the washer. You have them radiating out from the underside of the bolt head. All right? So this is where the frustra radiate out from, not from the washer. All right. We have the 30-degree pressure lines going down and eventually intersecting here. And we have to deal with three frustra. We have this pink material. This frustrum is entirely within the pink material, and it has a capital D, which is going to be equal to the 0.75. Okay, so there's the capital D there, same as it is above. And we've got a thickness of that frustrum, which is 0.6725, so that'll be, if we call that frustrum 3, that'll be T3, and this will be KM3. We've got a frustrum that comes down through the top plate material, and it goes to where the plates join. But here here's where the plates join. This is the plate joint. And here we have a transition from one material to the other. So we've got to divide up this top half into two different frustra. Let's make this KM1. It's going to use E of the top material. It's going to use big D of 0.75, and it's going to use a thickness called T1, which is not 0.6725, but the actual thickness of the top plate plus the thickness of the washer. Make sure my dimension line goes to exactly the right spot there. Okay, and then finally we have this third frustrum, which is the second lower material. It's going to have a big D equal to, so frustrum 2 is going to have a big D2, which is the top width of that deep fuchsia colored frustrum, and that'll give us a KM2. And the only way to get the overall stiffness is to sum these things in series. 1 over Km equals 1 over Km1 plus 1 over Km2 plus 1 over Km3. So the bolted joints, there can be a lot more calculation involved compared to the bolt stiffness calculation. If you have a gasketed joint, it depends on how the gasket is put in there. Here we have, in A and B, we have two confined gaskets. Well, a confined gasket and a confined O-ring. We still have, let's say, steel-on-steel contact. And for calculating the joint stiffness, we're going to basically ignore the gasket in A and B. And the joint stiffness will be a little bit lower because of the gasket, but it'll be pretty close to if we just take the steel on steel or aluminum on aluminum, whatever it is. For the unconfined gasket, we have Kg, we're going to have K1, and we're going to have K2. Now, if kg is much smaller than K1 and K2, then this term is going to dominate. Okay, and for an unconfined gasket, we can pretty much set the total joint stiffness equal to the gasket stiffness. That's especially true for rubber. There's a table here from another text from Norton, which has Young's modulus for some gasket materials. So there are going to be gasket materials like compressed asbestos or copper, which are, you may want to include K gasket in this calculation if you get into the copper ones. Okay, the copper stiffness term may still dominate, but it may be worth your while to put in the 1 over K1 and 1 over K2 for the plates. But certainly, and you can do these calculations yourself just to get a little bit more experience and intuition about it. If you get into the cork and the plain rubber, well, that's much softer than the steel. Often gasket makers will quote a gasket pressure that is required to ensure sealing. Okay, so there may be a minimum specified required sealing pressure. Now, the minimum clamping force you're going to get. Okay, you can tighten your pressure vessel lid with your gasket material in there, but it's not until you apply the separating force P that you can find the minimum clamping force. And when the clamping force decreases from the preload down to the minimum, that's when you've still got to have enough pressure to meet your gasket minimum required sealing pressure. Pressure is force divided by area. Now, the area is going to be gasket area per bolt. So if AG is the total gasket area and we have N bolts, pressure is going to be FM minimum divided by gasket area per bolt. Now, if I substitute this value of the minimum FM into that equation, then the pressure I need, this is lowercase p, is going to be Fi minus NP. And that's going to be actually the NL, I suppose, from our previous derivation. So Fi minus NL times P times 1 minus C divided by, actually, if I divide by AG over N, it's going to be the same as multiplying by N over AG. So, yeah, that's right. Okay, so that's how you can determine your gasket pressure, and that may have to exceed some minimum value specified by the manufacturer. So we have bolt stiffness, reasonably straightforward as long as you keep track of how much of the bolt length within the grip is threaded versus unthreaded. Joint stiffness, approximate 30-degree frustrum method from Shigley, works quite well. You may want to do FEA if you've got a supercritical application and if you've got a huge research budget. If you've got two materials that are the same, I would say including the material of the washer, then you can find your joint stiffness in one step. Otherwise, you may have to do it one frustrum at a time and then add those frustra stiffnesses in series to get your overall KM.